Okay, we're just about finished with the membrane potentials notes. The next thing to cover is how would a neuron get a second action potential? When can it get a second action potential? There is a period of time when the neuron is still busy from the first action potential in which it can't have another one, no matter how much stimulus is applied. Meaning, if you started the first action potential with a ligand, acetylcholine, binding to ligand-gated sodium channels, if the neuron is still busy from the first action potential, you can't get another one. That period of time is called the refractory period. You might have learned refractory periods if you've ever studied human sexuality, because there is a period of time after a climax in males in which no climax is possible, no way, no how. Okay, so let's talk about that in the context of neuron physiology. This also applies to other electrically active cells, but we're concentrating on neurons in this chapter. Okay, so here was our action potential. Okay, so remember we covered several times how you get to minus 70, which is what kind of channels? Leak channels. How you get from minus 70 to minus 55, which is what kind of channels? They're sodium because it's depolarizing. They're gated because I am not staying at resting membrane potential. And leak channels allow me to stay at resting membrane potential. Gated channels allow me to move away. And what kind of gated? Well, definitely not voltage gated, because that starts right here. So we said that we're going to look at these as ligand gated sodium channels. And then once I get to minus 55, from minus 55 up, these are opening voltage gated sodium channels. And then when I'm at the top here, you will close your voltage gated sodium channels and open voltage gated potassium channels as you start moving down here. Okay. And then you're going to have to pump everything back into the right position. So here's my question. In a neuron, this is one action potential, and a neuron has to finish the first action potential before it gets to the second one. There is a period of time in which you cannot have another action potential, no way, no how. And that is called the absolute refractory period. No way, no how. No second action potential can be generated, no matter how strong the stimulus. And I want to talk about why that is true. So let's go back to the video that we looked at last time. We don't have to watch the whole thing. But remember that these, in the video, these are your voltage gated sodium channels. They're in red. They've got a top gate and a bottom gate. And then these are your voltage gated potassium channels. So I want to look at this again.
This event marks the beginning of phase 1 of the action potential, known as depolarization. As sodium ions diffuse into the axon, the membrane potential becomes less negative. This causes more voltage-gated sodium channels to open, and the membrane potential soars to plus 30 millivolts.
Okay, so at plus 30, what is going to happen? What's going to happen is you're going to close your sodium and then open your potassium, and I'll put it back together with refractory period in just a second. Give me a minute.
At this point, two key events occur. The inactivation gates of voltage-gated sodium channels close
those.
And voltage-gated potassium channels open.
And now we're going down.
These two events mark the beginning of phase 2 of the action potential, known as repolarization. As potassium ions diffuse out of the axon, the membrane potential becomes negative again. However, the membrane potential continues in the negative direction, going beyond the resting state of minus 70 millivolts. This marks the beginning of phase 3 of the action potential, known as hyperpolarization.
Okay, so what I want to talk about is when could you at least theoretically get another action potential and when could you not? So look at the position of this sodium channel when I hit minus 55. So I had the top gate closed and the bottom gate open. And then I opened the top gate, and now sodium is moving in. So this is the figure from your textbook. So I'm sitting at resting membrane potential, and they draw them a little bit differently. So what's going to happen when I open one of the gates? I'm going to allow, this is basically opening your voltage gated sodium channel right here, which is the same that you're seeing right there. And then sodium can actually move in. I think we can agree that as long as this sodium channel is in this position, it's already open, it's already busy, you can't open it anymore. So even if I depolarized it again, I couldn't get it more open. So it's busy right here, okay? And likewise, once the inactivation gate closes, because I closed it close to positive 30, it's busy right there. And even if I opened the activation gate, I couldn't get any sodium moving in. So really what's going to happen is you are going to be in absolute refractory period as long as your sodium channels are not in their original position, because they have to be back to their original position with the inactivation gate open and the activation gate closed, so that if they hit minus 55, they would open and allow something in. Okay, so what does absolute refractory period have to do with? Absolute refractory period primarily has to do with the position of the voltage gated sodium channels. If the voltage gated sodium channels are inactivated, like they are here, or if they have not been completely reset, like if this is open or inactivated, you can't get another action potential, because action potentials have to do with voltage gated sodium channels. So really what happens is throughout a lot of the action potential, you are in what's called the absolute refractory period, in which you could not get another action potential no matter what. So on this diagram, what is happening in this blue portion right here is the voltage gated sodium channels are not completely reset to their original position. Therefore, you are in the absolute refractory period, and you could not have another action potential, no way, no how. Now, there is also another portion, and by the way, the absolute refractory period is really most of the action potential from minus 55 all the way almost back to resting membrane potential before you get all of those voltage gated sodium channels reset. Okay, but there is another portion right here that's called the relative refractory period, because it's relatively hard to get an action potential. What's happening during the relative refractory period is you have probably reset all of your voltage gated sodium channels, so you could have an action potential, but one of two things might be occurring. In this animation again, so once we get to the point that your voltage gated sodium channels are reset, but your potassium channels are still open, or this period of time in which you are slightly hyperpolarized, those portions of time, it's hard to get an action potential, but it's not impossible.
Action potential, known as depolarization.
So you're in depolarization.
As sodium ions diffuse into the...
So we want to go phase 2. Okay, so
the membrane potential becomes
down
negative again. However, the membrane potential continues in the negative direction, going beyond the resting state of minus 70 millivolts. This marks the beginning of phase 3 of the action potential, known as hyperpolarization. During this phase, voltage-gated potassium channels close and all...
Okay, so let's see if it makes sense to you that if either my voltage-gated potassium channels are still open or they close, but I'm slightly hyperpolarized, either way, it's going to be more difficult to get to minus 55 to threshold. Why? Because I'm letting sodium in, but I'm also letting potassium out if they're still open, so it's harder to move the number. Or if I'm hyperpolarized, I have to move it not from minus 70 to minus 55, but from minus 75 to minus 55. So This is what we call relative refractory period. It's harder to get an action potential, but it's not impossible. Okay, so if with this one, let's say if the original action potential was initiated by, let's say, 100 molecules of acetylcholine binding to 100 ligand-gated sodium channels, that got me to threshold. But if I were here, 100 wouldn't do it. Let's say maybe it took 150 or 200. So it's relatively hard to get an action potential in the relative refractory period. Okay, so now let's talk about action potentials and sort of the all or none nature of action potentials. Here's the deal with an action potential. By the way, a lot of times they simplify them to little spikes instead of showing the entire action potential. So here's the deal. If you have a sub-threshold stimulus and it doesn't hit minus 55, then you get no action potential. If you have a threshold stimulus, you get an action potential. So they are all or none. So when you hit threshold or when you exceed threshold, right? So you can hit minus 55 or you can hit minus 50, right? If you meet or exceed threshold, then you get an action potential. It proceeds to the end of the neuron without stopping. It's constant in magnitude, not meaning that it never changes, but it's going to be the same the first time, the second time, the third time the cell does it. But if you have a sub-threshold stimulus, then no action potential. So once an action potential is generated in a neuron, for instance, it's exactly the same as every other action potential in that neuron. So regardless of the initial stimulus, whether it was 100 molecules of acetylcholine or 1,000, the action potential looks the same. So there are no strong or weak action potentials, and that's different than graded potentials, because graded potentials can be strong or weak. So no strong or weak action potentials. Once generated, all action potentials in a cell are the same as all other action potentials in the cell, which brings up a question. So if all action potentials are the same, how do you convey via the nervous system intensity? How do you say that hurts a little versus that hurts a lot? That smells really bad versus that smells kind of bad, right? That is hot versus that is warm. How do you convey that information? Well, it's actually with the frequency of action potentials. So again, this is a simplified action potential. Again, all or none says subthreshold stimulus, no action potentials. Threshold stimulus, action potential. But what about if you start getting way more of a stimulus? Like, what's the difference, theoretically, if I could do it, between poking my finger with a pin and the amount of action potential versus cutting my blasted finger off, if you could control for the number of neurons that were being stimulated? I'm not trying to involve more neurons. One neuron, what's the difference? The difference is really this. Poke my finger with a pin, I get action potentials that kind of go like this. They go pain, 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 because it's not a very strong stimulus, so I don't have very frequent action potentials, versus cut my damn finger off, the same neuron would be going pain, 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 as fast as it could, okay? As fast as it could. So this is called frequency coding. This is an important concept. It follows us all semester long. Information about a stimulus strength is conveyed to the brain by the frequency of action potentials, not the strength of an action potential. So the stronger the stimulus, the more action potentials, not the bigger action potentials. And that's super duper important. So let me show you a couple things. Now, for those of you who are flowchart people, which isn't in my experience very many of you, this is a great flowchart that sort of shows you.
I'm having trouble hearing you.
Sorry, shut up, Siri. This is a great flowchart that goes through this with you. If you're not that kind of person, that's fine. There is also this interactive activity. This comes with the digital content with your textbook. So hopefully you will be able to access it through your notes. If you haven't, you may have to buy digital access. I tried to link it in a way that you could get to it, but we'll see if it works. So if you click on this, it's fantastic. This again is interactive physiology. For those of you who are kinesthetic You need to practice these things in order to activate sort of your real way of learning. So if you click on this and go here, let me just show you a little bit. I'm not going to go through the whole damn thing with you. Okay, so what it is going to do is, so all of this stuff in white is just stuff you can read and watch. But once you get down to the ones that are in green, number 5 here, for instance, it will allow you to manipulate something. And this is manipulating in a way that teaches you this same concept. Action potentials are all or none, this same concept. So let me just show you how this works so that you will be encouraged to use your time to do this. All right, so let me show you. All right, so tap or click the depolarize neuron button to depolarize the neuron. So I'm going to depolarize it. It's going to ask me a question. Will action potential be generated? Nope, that's subthreshold. Yay! And I don't, oh, I thought that was a hot dog, but it's a voltage gated sodium channel. I was like, why are they using hot dogs? Okay, now that we'll do it again. It is a little slow at first, but it gets harder, I promise. So I got that one wrong, and it redirects me. Okay, so let's see what happens again. So I'm going to depolarize this neuron. Will this action potential be, will an action potential be generated? Yes. Okay. At minus 55, you'll get an action potential. Start going, right? And then tap or click threshold. Mine's kind of covered up because I've got the window squashed. Then it will show me what's going to occur. So this was just generating the all or none, or demonstrating the all or none thing. But it gets harder. And all of these are activities, states of the voltage-gated sodium channels during an action potential. Ooh, pufferfish. I like talking about pufferfish. Green mambas. And the quizzes are not easy here, which is good because it redirects you. So I think interactive physiology is fantastic, and I would highly, highly encourage you guys to use it. I think I've linked it in such a way that you might be able to get away with it without buying the digital content, but if you can't get to it, that's why. So I don't test off of it, but it reinforces exactly what I've been talking about, which is why I linked to it. Okay, so we'll stop there, and then I'll talk about myelinated versus unmyelinated axons, and then some disorders.